In this video, I will walk you through configuring a connection to an Enron Modbus EFM device using the top server, which is common in the oil and gas industry for electronic flow measurement throughout the various stages of collection, distribution, and transport of oil and gas. I will cover the channel and device setup, including the EFM settings, give a summary of the settings that will be encountered, and when it is appropriate to change them from the default values. So I have my top server configuration open, as you can see here. Now, the first step in configuring a connection to an Enron Modbus device from top server is to create a channel. So I want to click to add a new channel. Now, a channel represents a communication link from the PC running top server to the device. In the case of the Enron Modbus driver, the channel can represent the serial port when using serial devices, or the socket connection over which Ethernet communications will occur. First, we need to select the Enron Modbus driver from the list of available drivers. Select my Enron Modbus driver, and then I'm going to click Next. Now, the channel name is user configurable and will be how the channel appears in the top server tree view, and is also how clients will reference devices configured under this channel. For demo purposes, I will simply call my channel Enron. Click Next, and I need to choose whether or not this channel should be included in a virtual network, and if yes, which virtual network the channel should be assigned to. So by default, virtual network is not used. So I can specify that this channel belongs to up to 50 different virtual networks. Now, virtual network being a way to serialize multiple channels that are using different protocols, which is important in the telemetry situations where your target site that you're communicating with might have more than one type of actual communications protocol. So I'm going to leave that at none. If I were to select a virtual network, the transactions per cycle specifies the number of single read-write transactions that can occur on the channel. When a channel is given the opportunity to communicate, this number of transactions is attempted. For the purposes of this demo, I'm going to leave all the settings here at the defaults and click Next. Now we need to select the appropriate connection type for this device. If using a serial connection, the serial port settings, you leave COM port selected here, and the serial port settings such as your COM ID and the baud rate, data bits, parity, and other serial parameters must be set to match those of the actual device. Select Ethernet encapsulation. If Ethernet encapsulating the traffic, you specify which network adapter the top server should use for communications. So for the purposes of this demo, I'm going to leave this set to Ethernet encapsulation, as I've selected here. And I'm going to leave the network adapter at the default, which allows the operating system to select the appropriate NIC based on the device's IP address that gets specified later in the device properties. So go ahead and click Next. And now we just need to configure the connection behavior. So the setting close connection when idle will terminate the connection when it's not in use for the specified number of seconds. If you were to set that to disabled, then the connection will be maintained whether it was idle or not. We want to leave that enabled. Idle time to close defines how long the period of disuse is before the driver should terminate the connection. We're going to go ahead and leave both of these settings at the defaults. Click Next, and here we review the write optimization settings for this channel. Now, these settings determine the optimal method of writes based on the write queue and the priority of write operations to read operations. These are generally going to be left at the default, but can be altered as needed. We're just going to leave this at write only latest value for all tags with a duty cycle of 10. That's generally the best way to go when you're starting out. If you find those need to be changed later because you have different write priorities, then you can come back and change those at any time. So now we need to review how the driver is going to handle non-normalized floating point values. This is pretty well generally just left at the default value of replace with 0, unless non-normalized values are expected, such as a value that's not a number or a value that's infinity. So we'll leave that at the default. Click Next. You can also specify an inter-device delay if desired. This setting determines whether the channel will pause after receiving data from a device before switching to the next device on the channel, and it will specify how many milliseconds this pause should be. This setting can be particularly useful in telemetry scenarios if the radio requires time between requests. For the purposes of this demo, we'll go ahead and leave the inter-device delay at the default of 0 and click Next. The last dialog you see here summarizes the selected channel settings, and as you can see, it also provides the ability to tweak the settings right here in the summary without having to go back to the previous sections if you notice something's incorrect. So if, for instance, I decided I wanted to change the physical medium back to COM port, I could do that here instead of having to go back to that specific section. Now, since all of our settings are correct, I'm going to go ahead and click Finish to finalize the configuration and create my channel. You'll see there my Enron channel is created. Now that the channel is complete, we need to add a new device to the channel. So I'm going to click Add a Device. And the device name is user configurable, just like the channel name was. And it's how the device appears in the top server tree view, and also is a component of how client applications will access the device. For this demo, I'm just going to call my device meter1 and click Next. Now, the Enron Modbus driver has two different models that you can select here for the model field, either standard or extended station ID, depending on what your device supports. Now, with standard station IDs, the address field in the Enron Modbus request is 1 byte long. So it's going to support a station or device ID range of 0 to 255. Now, with extended station IDs, the address field in the Modbus request is 2 bytes. So it's going to support a station or device ID in the range of 0 to 65,535 because of that. Now, which one your device requires is going to be determined by the device manufacturer and how they've implemented the device ID. So you'll want to consult the manufacturer's device documentation to see whether your device is using a 1 byte long or 2 byte long station ID field. For the purposes of this demo, we'll keep the model as standard, which means our device ID is going to be in the range of 0 to 255. And I'm going to go ahead and click Next. Now, here we specify the numeric format of the device ID and the device ID itself. Now, even with Ethernet encapsulation, the target Enron device should still have what is sometimes called a device ID, station ID, or sometimes it might even be referred to as a node ID or node address. Now, the ID format defines whether the number you specify should be treated as decimal, octal, or hexadecimal format. Which one of those is correct depends on your device, and you should be able to determine this either in the manufacturer's device documentation or the device's settings. We're going to keep the default of decimal, and I'm going to leave the ID at 1, so it'll be a decimal 1, and I'm going to go ahead and click Next. Now we need to specify the device's scan mode settings for subscription-based client applications. In systems where bandwidth utilization is not a concern, this setting should be left at the default, which is respect client-specified scan rate. Other options include, I'll just click my drop down so you can see what the options are. The default respect client specified scan rate simply respects the requested scan rate from the client application to determine how often to scan the device. So OPC client applications, for instance, are going to specify the update rate for the OPC client group, which determines how frequently the actual device should be polled for data. So if you leave the setting respect client specified scan rate, we're going to respect that setting from the device. Request data no faster than scan rate setting sets a ceiling. Data will be requested no faster than the specified time frequency. The setting request all data at scan rate means all data will be requested at the specified timing frequency. Setting it to do not scan demand poll only means there will be no automatic scanning done of the device unless a plugin or a client application manually triggers the poll. And there's a special _demand poll system tag for each device that makes that possible. And last but not least, the respect tag specified scan rate option respects the scan rate that's defined at the individual tag level, and that's only going to be applicable when you define static tags in the top server configuration. So for our purposes of the demo, we're going to go ahead and leave the scan rate at the default of respect client specified scan rate, and go ahead and click next. Now we need to specify the actual IP address, port, and whether the connection should use TCP/IP or UDP as the transport. So for my IP address, I'm going to go ahead and enter 192.168.111.50 for my IP address. And I'm going to keep the default port of 2101, which is what's would be configured on my device. And that is a common port. One of the other common ports for Enron Modbus is 10,001. You might also see a port of 502 because that's the standard Modbus port number. You'll want to check your device for the specific port number it is configured to use, because the majority of devices do allow that to be configurable. So you want to make sure that you're specifying the port number here that the device is actually configured to use. And we're going to keep the default of TCP/IP, which is the most common transport that's being used for this protocol. Go ahead and click next. Now the timing settings here, and I'm going to expand this because they do scroll off of the page to make sure we cover everything. The timing settings should be set appropriately based on the type of connection and the level of congestion on your network. Now, these can generally be left at the default to get started, and then you can either increase or decrease these as needed. For instance, if you're seeing a lot of connection timeouts to the device, or actually making the socket connection to the device, you may want to increase the connect timeout that you see here from 3 to a larger number of seconds to give the device more time to accept the socket connection. Now, if you're getting connected but you're seeing a lot of timeout waiting for response to your actual requests, you may need to go in and increase the request timeout setting from the default of 1,000 milliseconds to give the device more time to respond to the requests. Now the goal is to have the timing settings as low as possible while still maintaining successful communications. This allows the driver to detect actual communication issues more quickly. Now the last setting you'll see here, you can also specify an inter-request delay, which is going to insert a delay between requests to the device. This can be useful for slower devices where it's necessary to give the device more time between requests to prevent overloading the device. For our purposes, we're going to maintain all the defaults for these settings. We'll go ahead and click next. Related to the timing settings, here we have auto demotion settings, and these are going to determine whether unresponsive devices are going to be taken out of the polling cycle for a specified period of time. So just so you can see what I'm talking about, I'm going to go ahead and enable this so you can see all the settings. Now you'll see here you can specify a number of timeouts. So after the device is timed out this number of times, once it's gone through the number of retries from the previous screen, that's one timeout. So this determines how many times it should be able to go through the timeout period before it gets demoted. Then once it's demoted, the demotion period is the amount of time to keep that device out of the polling cycle before it ever gets tried again. Now, in situations where multiple devices are configured under a single channel, now that's normally going to be the case in a telemetry or a multi-drop serial scenario. It is recommended to enable auto demotion, and you'll see at the bottom here, discard request when demoted. It is recommended to enable that setting. To discard write requests on devices that are written to frequently during auto demotion. Otherwise, any write request is going to override the auto demotion period and attempt a connection immediately. Now, since devices under a channel are treated sequentially, having this setting enabled will prevent a down device from repeatedly slowing down communications for other devices on the channel that are still communicating normally. Now, for our purposes, since there is only going to be the one device on the channel, I'm going to go ahead and set this back to disabled, which is the default state, and go ahead and click next. Now we get to specify the automatic tag generation settings, namely if and when a static tag database will be created, how previously generated tags will be handled, and if tags should be included in a specified parent tag group. A parent tag group setting specifically keeps automatically generated tags from mixing with tags that you may have entered manually. When enabled, tags will be created in the server for registers that are mapped to EFM configuration attributes for each enabled meter in the device. Now, we're going to go ahead and leave these settings at the default and click Next. Now we need to specify the time zone that the device resides in, and whether the device time should be synchronized with the system time of the machine the top server is running on, and also whether or not to respect daylight savings time. Now, whether or not to respect daylight savings time depends on whether your device is already set up to respect daylight savings time or not. So, time zone's easy. This needs to correspond to the time zone where the actual device is located, which could be different from the machine where your top server is installed. So, I'm going to leave that at the default of Eastern time because that's where I'm located. I'm going to leave respect daylight savings time set to no. And as far as the time sync method goes, you've got a couple of different options to choose from. Disabled means that the timestamp of the device will never be synchronized with the top server system clock. Absolute is when the timestamp of the device will be synchronized once per day at the specified time. So you set it to absolute and you specify time. So the default is midnight. So if I set this to absolute and a sync absolute of midnight, then my time is going to sync every day at midnight. Then there's the interval time sync method. And I've got my sync interval down here. The timestamp of the device will be synchronized on startup and at the specified time interval. So by default, it syncs the time every hour, so every 60 minutes. So it'll sync on startup. So as soon as we start communicating with the device, there will be a time sync, and then after that, every hour there will be another time sync. The last option is the on-pole time sync method, and with this method, the timestamp of the device will be synchronized only when an EFM poll for the device has been completed. So you see, there's no other parameter associated with that one. Now, the time synchronization settings are intended to prevent the device clock from drifting too far from the top server system clock and will primarily affect EFM record polls, so not real-time data collection. Now, for all of the methods, you probably notice this time sync threshold setting. So it's possible to define a time sync threshold, which, when this is set to a value other than 0, allows the driver to compare the device and system times, and when the difference is greater than the specified value, the driver will perform a time sync. This ensures the drifting of the device's clock is never greater than a defined amount. So for demo purposes, I'm going to set this to absolute, and I'm going to leave that at the default of midnight with no time sync threshold. I'm going to go and click Next. So now we need to specify the data encoding settings as appropriate for the specific Enron device. These settings pertain to byte, word, and bit ordering. And you'll see that I've got a scroll here, so I'm just going to expand this so that we don't have to scroll so much. So you see there's a setting for Modbus byte order, the word order, and also bit addressing and bit ordering. So these settings affect how the value of a register is interpreted by the driver. The default settings are generally the best place to start unless your device's documentation specifically indicates a byte word or bit order that differs from the default. You've got zero-based bit addressing is enabled by default. So that means bits within a register would be 0 to 15. If your documentation says your device has bit addressing from 1 to 16, then you would disable this particular setting. Now, this is also the section where the specific registers for the real-time clock in your device are specified, and that corresponds to those time sync settings. So you'll notice there's a register for each component of the timestamp. So here you specify the register in the device that corresponds to the hour, the minute, the second, the year, the month, and the day. So each of those is stored in a separate register. The default registers specified here are the most common for each field, but you can confirm that these are correct by comparing to your device's own documentation. We'll keep the defaults for all of these. I'm going to go ahead and click Next. Then we specify the block sizes that should be used to read contiguous registers from the device. These, so you see you've got the Boolean variables block size and the numeric variables block size. These indicate the maximum number of numeric registers and Boolean values that will be read from the device in a single request. In telemetry situations, these should be increased to reduce the number of requests. The maximum number of Booleans is 2,000, and the maximum number of registers is 125 per request. So I'm going to set this to 2,000, set this to 125. Now, the defaults are normally fine for initial testing, but you want to determine what the smallest block of contiguous addresses is in your actual device, and then specify that value here to maximize your efficiency and make sure you're making the smallest number of requests possible to service the data that you're requesting. So I'm going to go ahead and click Next. Now we specify whether Modbus TCP framing should be used. This is disabled by default. And this option is only available if you're using Ethernet encapsulation. And when it's enabled, it appends the Modbus TCP MBAP header to the beginning of any request. Now, this is a very specific setting. Generally, Enron Modbus devices don't typically use Modbus TCP framing, so unless your documentation says otherwise, it's generally recommended to leave this at the default, which is disabled. Now, you can also specify whether there are any leading or trailing bytes that are going to be included in the response, which is sometimes necessary with certain radio telemetry. You'll see that certain radios will include leading or trailing bytes, and you need to account for those in order for the driver to properly process the actual Modbus response that's inside that. So if you're not sure, it's best to just leave these settings at the defaults and click Next. You can also specify how TopServer should handle situations where the device indicates we are referencing an illegal tag address. So that's going to be, you'll get back either an error code 2 or an error code 3 for the Modbus response. The setting's enabled by default, so TopServer will deactivate the erroneous tags and not waste time trying to pull them again when this is left at the default. And when the reject repeated messages option is enabled, the driver will reject repeat response messages. When it's disabled, which is the default, this option will treat repeated messages as an invalid response, and it'll go ahead and retry the request until it gets a valid response, or until we time out based off of the timing settings specified earlier. So we're going to go ahead and keep the defaults here, which is normally best, and click Next. Now we can configure the meter-specific archive configuration options. For the max hourly record setting, this specifies the maximum number of hourly records the device will store. It defaults to 1,080, but it supports up to 65,535 based on what your specific needs are. Then you get the max daily records, and that specifies the maximum number of daily records the device will store. And it defaults to 35, but it also supports up to 65,535. Again, what this is set to depends on what you're typically going to need. It's going to be specific to your scenario and your device based off of how many maximum records you want your device to store. Same is true with max event records. This specifies the maximum number of event records the device stores. And it defaults to 1,000, but it also supports up to 65,535. And you can also specify whether or not the starting point for your archives is 0 or 1. 0 based is disabled by default, so the default starting point is going to be 1. And for your specific device, the starting archive is 0, then you would need to enable this. Then we have the record order. You'll see this is grayed out. This specifies the order that records will be stored in the device. Now, changing this setting from the default value, which is ascending by default, is not currently supported. So it can't be changed to descending instead of ascending. Ascending is the default, and that's what it has to stay with. Also, you'll see the record buffer type is also grayed out. This specifies the type of buffer that the device will use to store records in the device. Changing this from the default value of wraparound was not currently supported. So I'm just going to scroll down. Then we have the pointer value setting. This specifies whether the value in the hourly and daily pointer registers should point to the last stored value or to the next available register. The default, as you can see here, is last stored. So you'll need to determine if your preference is last stored or, as you can see here, next available. Then we have the non-metered events settings. This specifies how to handle events in the EFM device not associated with a specific meter. The default logs only to meter 1. As you can see, meter 1 selected here. If I do the drop down, other options are either you can ignore the non-meter events completely, you can log them to all of the meters, or you can specify another meter that you want those to be logged to other than meter 1. We'll just leave that at the default of meter 1. And then you have several different offsets. You get a bool offset, a short offset, a long offset, and a float offset. For these offsets specify the offset of each data type configuration register range for each successive meter. The defaults are the most common offsets, but you should consult your device documentation to confirm the defaults match the requirements of your device. So you'll see the Boolean offset starts at 100, the short offset is 100, the long offset's 100, and the float offset is 250. So those are what we've seen most commonly, which is why those are the defaults. But again, you'll just want to consult your device documentation to make sure those match up with what you need your offsets to be. So I'm just going to scroll down. Now we've got settings for your history archive Modbus byte order and the first word low settings for the history archive. These settings are similar to the ordering settings we specified earlier that applied to real-time data in your Enron device, but these are specific to the EFM history archive on the device. The defaults are the most common unless your device documentation specifically indicates the ordering should be different for the history archive. Then similar to that, we have settings for the event archive Modbus byte order and the event archive's first word low, so the word ordering. And again, these settings are like the ordering settings we specified earlier for real-time data, but these apply specifically to the EFM alarm and event archive on your Enron device. Again, the defaults are the most common. Unless your device documentation specifically indicates the ordering should be different, you should leave these at the defaults. And then we have the multi-byte character setting. Now that specifies whether the configuration string data is stored in 2 bytes per character format or not. The default is enabled that the configuration string data is stored in 2 bytes. So again, I would leave that enabled. That's the recommended setting, unless your documentation tells you that the configuration string data is not stored in 2 bytes per character. And then we have the history record time and the history record date stamp formats. Now the Enron Modbus data type for history record time and date stamps is a float. These settings specify whether the time is stored in the hours, minutes, seconds format or the hours, minutes, dot seconds format. And whether the date time stamp or the date stamp is month, date, year, or year, month, date. Now, same thing with the event record time and event record date stamp formats. You specify whether the timestamp is hours, minutes, seconds, or hours, minutes, dot seconds. and whether the date stamp is months, days, year, or year, month, date. We'll leave those at the default. And last but not least, in this section, we have the clear cache setting. When clear cache is set to yes, the top server will clear all EFM data and reset the EFM pointer files, which are used to keep track of the EFM uploads. All EFM data will be repulled from the device, so we'll go back and we'll retrieve everything that's stored on the device instead of just the latest data. And then after that point, this setting goes back to disabled. It toggles back to disabled. Now, the use cases for clearing the cache are during testing, or if the EFM mappings are found to not be configured correctly, so you want to go back and repull everything with the correct mappings, or in situations where it's needed to re-request the entire EFM archive from the device. So maybe your reporting application, whether it's FlowCal or PGAS, maybe somehow the files, maybe the files were corrupted or lost somehow after the fact. And you need to retrieve the EFM data from the device, then you can clear the cache and make that possible. We're going to keep the defaults for all of these and go and click Next. Now we can review the device settings in the summary for correctness and make any necessary tweaks. Now, all our settings should be correct here, so I'm going to go ahead and click Finish. Now that our device is created, you'll notice 3 additional configuration sections in the tree view under our device. We've got address ranges, EFM mappings, and EFM meters. So I'm going to step through those. For address ranges, if I highlight that section, you'll notice there's a default defined range for each data type. So there's a Boolean range, a short range, a long range, and a float range with a starting address and an end address. Now, the defaults correspond to typical ranges for each data type, but you can consult your device documentation regarding address ranges to confirm these are correct and adjust them as necessary. You'll notice that each range does not overlap the next, as they correspond to consecutive addresses in the Enron device. So you'll see that Boolean goes from 1 to 2,999, short starts at 3,000, goes to 4,999, long starts at 5,000. And so on and so forth. You'll see they don't overlap with each other. They're contiguous. Now, just so I can show you what this looks like, if I open the range for Booleans, double click there and open the range for Booleans, you'll notice that you specify device data format, and that's just going to be your data type. So Boolean, short, long, float. And then along with that, you specify a start address for the range and an end address for the range. And then a base address if your device requires a base address. Should be used if the device expects the address in read and write request to be a data address rather than a coil or a register number. So we'll just leave that at 0. You can also specify the corresponding Modbus function code to be used for reading and writing the range. So this is a Boolean. For Booleans, a read function code is either going to be a 1, and you're going to use a function code of 1 if the range is a block of output coils, or 2. So you're going to use a read function code of 2 if the range is a block of discrete inputs. I'll leave that at the default. And for the write function code, acceptable options are 5 or 15. So a write function code of 5 should be used for single Boolean writes, or a function code of 15 should be used if you're writing to multiple Booleans in the same write request. Some devices only support multi-write function code of 15. So you'll need to see what your device supports specifically so that you can set that appropriately for your ranges. So I'm going to click out of that and take a look at one of the registers ranges. See again, device data format set to short, starting address 3,000, end address 4,099 with no base address. And for register type addresses for the function codes, and that's basically going to be anything other than a Boolean. So that's going to apply to your shorts, your longs, or your floats. So valid function codes for reading are 3 or 4. So a function code of 3 should be used if the range is a block of holding or output registers, and a function code of 4 should be used if the range is a block of internal or input registers. And for writes, the write function code options are 6 or 16. So a function code of 6 is going to write to a single register, and a function code of 16 is going to be used for writing to multiple registers in the same write request. So as I mentioned earlier, it's possible for some devices to only support one or the other of those function codes, which is why being able to select that is important. A lot of times you'll see a Modbus device only support the function code for multi-write or function code 16. So trying to write to a single register with function code 6 would fail for that type of device. So it is important to make sure of what your device supports so that that's selected accordingly. So we're going to go ahead and leave the address ranges here at the defaults, and we're going to move on to the EFM mappings. The EFM data, which consists of configuration, history, alarms, and events in your Enron device, must be mapped to the server's EFM attributes. The EFM mapping dialog is used to configure these mappings, which can then either be shared by all meters, a subset of meters, or uniquely per meter by specifying which mapping to use when we get to configuring a meter in our next step. So you'll see there's a default EFM mapping here. Now, there's no limit to the number of unique mappings you can define. So this is one. You could define additional mappings by right-clicking, selecting New Mapping to create an additional one. And a mapping is only actually used if it's selected in a meter setup. So I'll show you that shortly. Now, when we highlight, as you see here, when I highlight the default EFM mapping, you'll see I've got low and high states alarm mappings for temperature, static pressure, and differential pressure for a meter. Now, if I open up one of the alarm mappings, it's going to open up my low state for temperature. You'll see the address field corresponds to the actual Enron address in your device that represents this particular alarm. Now, you'll see this has B. Specifying B at the beginning makes it a base address, meaning the alarm is meter specific. The offset corresponds to the data type offsets defined earlier in the device properties and determines which meter the alarm corresponds to. However, if this was just 3106 without the B, the alarm is no longer meter specific, it's static. And if we received an alarm for 3106, then it would be sent to all meters using this particular mapping. Then we have the type. Then we have the type field, and that determines what type of alarm the mapping is. So I'll just expand this. As you can see, the different available options are differential pressure, static pressure, temperature, cutoff, backflow, or battery. I'll leave that at the temperature. And then you have the state field. So it's just that. The corresponding state is defined in the device for an alarm, for the particular alarm that you're measuring. So possible options are off, on, high, or low. So we'll leave that at off. Go ahead and cancel out of here. So those are the alarms. Now if I open the properties of the default mapping group itself, so I'm going to right click there and open the properties. You'll see we can also configure the address mappings for EFM configuration information here on the left. EFM history as well. So if I select configuration, the configuration section is where addresses are mapped for configuration parameters such as the actual meter ID, meter type. So that's going to be such as whether it's an orifice meter, Coriolis meter, etc. The pressure-based setting or pressure-based parameter, the calculation method being used, many other variables. As you can see, it's an extensive list, and it's as you can imagine, it's vital that these mappings be correct and mapped to the appropriate addresses in your Enron device for these specific parameters for proper EFM collection from your Enron device. History data pulled from the Enron device is in record format. So let's go over to the history section here. Now, each record that's being retrieved from the Enron device for the history data contains an array of 4-byte floats. Each float has a unique index or position in the array. The history section maps the correct array index of each float to the specific corresponding EFM attribute. So you'll see here it's going to map attributes such as flow time, average pressure, average temperature, differential pressure, average extension, C prime, liquid mass, liquid volume if you're measuring flow of liquid instead of a gas, total volume, total energy, and you've got all sorts of different parameters for gas composition parameters, viscosity. Now, all of these mappings are specific both to the device manufacturer and how your Enron device has been configured specifically. So you want to consult your manufacturer's documentation and the actual device configuration or programming software for the different parameter mappings to determine the available alarms and parameters that are available and that need to be mapped appropriately here in the EFM mappings in Top Server. Now, last but certainly not least, I'm going to cancel out of here and leave those at the defaults. Now we're going to move on to the specific EFM meter configuration. So I'll expand that. As you'll see, I've got 12 meters configured here. It's possible to access up to 12 EFM meters in an Enron device. By default, only meter 1 is actually enabled, and then you can enable the additional meters based on your specific device configuration and meter availability, and the ones that you need to actually collect EFM data from. So if I go ahead and double click it to open up my meter 1 so we can look at the settings that are available, I'm just going to expand that so we don't have to scroll. The meter name is just a user configurable descriptive name for the meter, and you can do an optional description. Which driver is in use by this particular meter, whether whether this meter is actually enabled for EFM bowling or not. So like I said, meter 1 is the only one that actually is set to yes for enable by default. Meters 2 through 12 would all be set to no here currently. Then you get to the hourly archive, and that specifies this meter or run's hourly archive address on the device. So again, that's going to be a specific address in the device that corresponds to the hourly archive. Same with the daily archive. It specifies this specific meter or run's daily archive address in the device. And you get the hourly GC data setting. That specifies this meter or run's hourly archive address for gas chromatography in the device. The daily GC data, similar, that specifies the meter or run's daily archive address for gas chromatography in the device. Then you got your hourly pointer. This specifies the register in your device that's used to indicate the position of the current or last hourly record in the buffer. Now, whether it's current or last is going to depend on which option was selected for the pointer value setting in the device configuration earlier. Then you've got your daily pointer, and that specifies the register that the device will use to indicate the position of the current or last daily record in the buffer. Again, that depends on which option was selected in the device configuration earlier for the pointer value setting, whether it was the current or the last record. Then we've got the event counter. This specifies the register that the device will use to indicate the number of alarms and events records in the buffer. And last but not least, we've got the mapping, and this specifies which of the configured EFM mappings should be used for configuration history and alarm data. And that corresponds to that default, which is the only one that's currently configured. So if we configured more than one EFM mapping, then you'd have different options you could select from. You could use the same one for all of your meters. You could have a mapping configured for each separate meter. You could have a mapping configured that you use for a handful of specific meters. It's all fully configurable based on the needs of your specific device and the meters that are configured in that device. Now again, only the first meter is enabled by default. If your Enron device has more than one meter from which you need to collect EFM data, you'll need to enable and correctly configure one of these meters for each meter in the device. I'm going to cancel out of that, leave that at the defaults. Now lastly, you'll see I can click to add a static tag. Static tags can also now be configured in the server if so desired, or you can do what we refer to as dynamic addressing from the client application for this particular device. If you do dynamic addressing, then you just specify the address instead of a tag name. So 30,001, for instance, like if we look at our address ranges, if we wanted to access a short data type and address 30,001, you could specify 30,001 as your item name in your client application instead of having to define a static tag in your top server. For help with the proper addressing syntax, it's always recommended to access the Enron Modbus driver help file section on addressing for the specifics of what's supported there. This video has shown the general steps required for quickly configuring an Enron Modbus device in Top Server version 6 for EFM and real-time data collection. Now, it is not intended to be a comprehensive how-to regarding the Enron Modbus driver, and the Top Server Enron Modbus help file should be referenced for further information. While EFM meters were set up in this video, the Top Server EFM exporter plugin help documentation should be referenced to set up scheduled EFM polling and exporting to the desired EFM format.